Dersten önce sorusu olan var mı? Sınav nereye kadar olacak? Yani, sınav phase lead lag design dahil olmayacak. Yani lead kompansatör design, lag kompansatör design bunlar dahil değil. Faz margin, gain margin, phase crossover frekansı, gain crossover frekansı, bode plotlar, ondan sonra polar plotlar bunlar dahil. Ama lead ve lag kompansatör yok. Root locus mu? Yani. Bu dersin ana konusu root locus. Yani zaten yani yani bu dersi bitirdikten sonra Nyquist benim bile aklımda kalmıyor. Sizin nasıl aklınızda kalsın? Yani her sene anlattığım ders. Buyurun.
Sınavda bode plot olması durumunda bir template verecek yoksa kendiniz?
Genellikle şu şekilde bir plot giriliyor. Eğer şey olursa, bode plot çizmeniz istenirse bunun boşu verilir. Anything else? İlk konular şu şekilde. Yani tabii ki oturup da böyle modelleme falan gibi bir şey beklemeyin. Ama yani işte settling time nedir? Bu sistemin settling time nedir? Bu sistemde steady state error nedir? Bunlar tabii ki birinci midterm konuları ama bunlar her kontrol probleminde performance requirement olarak çıkan şeyler. Bunlara tabii hala bir hakimiyet bekliyoruz. Ama tabii ki oturup da kütleli bir yığın mass verip bunun modeli ne diye birinci midterm konusu çıkmaz. Okay. So today's topic is graphical phase lead lag design. Okay? So graphical design. So I have uploaded these notes to OTTI-class EE302 section 1. Okay, so you can reach these from there. And in these notes there is one thing written on the first page. Please do not try to find the transfer function g of s from the bode plot in graphical design. Okay, so getting such a bode plot, you are not required to write the transfer function from this. Okay, so we can design our compensators based on only the bode plot. You do not have to find any transfer function from the bode plot. Okay, so that might be the number one rule. If from this, if you want to extract the transfer function, if you do that, then you're going to get a wrong transfer function at the end. You might have some parts of that transfer function correct, but it's going to be quite inexact. Okay? And that actually means that we never try to extract the transfer function from a given bode plot. What does such transfer function mean? We have a control system. The control system architecture is given like this: GC of S, and I have G of S here. Okay? That is, we have this control system. All right? And this body plot shows only g of s to you. Okay, that is the plant for which we're going to design our compensator. So here, this is the body plot of g of s. So one of your friends asked me, what is the relationship between this one and the Nyquist plot? What might be the relationship between this one? So can I draw a Nyquist plot for g of s based on this thing?
You can do all the plots.
Yes, I can actually start with some axis here, real of s, imaginary of s here. And we see that this plot starts, the magnitude starts from where? Plus infinity, okay? And the angle starts from minus 180 degrees. So this Nyquist plot is going to start from here. Infinite magnitude, minus 180 angle. Then the angle goes to minus 160, etc. So this thing is going to come somewhere here, so that the angle comes to minus 140. Okay. When the angle comes to minus 140, it is going to go in the reverse direction, and we are actually going to cross the minus 180 degrees. While this is happening, we are actually reducing the magnitude still. And the magnitude is still decreasing. Where is the magnitude going? Minus infinity, meaning that it's going to zero in linear scale. And where the angle is going to go? Minus 270 degrees. So here is how the polar plot of this thing is actually seen. So if you this is a type 2 system actually. It is starting from minus 180 degrees. So if you look at this Nyquist plot, half of it is going to be looking like this. And if I complete this thing, it's going to be looking like this. Okay? So here there is a relationship between the body plot and the Nyquist plot. Nyquist plot is just the polar plot of the body plot. In body plot we separate the magnitude and phase. If you mark those in the complex plane, the magnitude is marked as the distance here. This is the magnitude, and the angle is marked as the argument of this thing. And then you can draw a body plot. You can draw a Nyquist plot from the body plot. Yes.
Why did you neden sonsuzda sıfırdan eksi 180'e kadar hepsi tarafında?
The reason is the following. When we try to draw the body plot, this system is actually looking like this. G of s. If I look at the slope here, when I look at the slope here, it is minus 40 dB per decade. When the frequency increases 10 by 10, then the magnitude decreases 40 dB. So when I look at this G of s, there is going to be an s square here, okay? And all of the other poles are going to be looking like this. 1 plus T1s, 1 plus T2s, going like this. I really do not know how many poles this would have. And I have 1 plus tau 1s, 1 plus tau 2s. I don't know how many zeros the transfer function is going to have. And I don't know their places either. And there is a k internal here. There might be a gain. Okay? This actually means that at low frequencies, since I will be able to neglect these, at low frequencies, this transfer function is going to be looking like k internal divided by s squared. And when I look at when I try to draw the Nyquist plot here, I'm going to come up with a Nyquist path, which is looking like this. This part here corresponds to the polar plot that I have drawn. This is the polar plot, okay? So this part of the Nyquist plot is polar plot, and it's the frequency response of G of s, okay? But this part is going to be at infinity, okay? This part is e to the j theta, epsilon e to the j theta, okay? From A to B, S is equal to epsilon e to the j theta. When theta changes, it starts from 0 and it increases into 90 degrees. Okay? And when I substitute epsilon e to the j theta in this transfer function, and when I let epsilon go to 0, all of these terms will turn to 1. Okay? All of these are going to turn to 1, and I will end up with only these type of terms. And when I substitute epsilon e to the j theta there, I will get epsilon squared and e to the j 2 theta. I will substitute s given like this, and it's going to turn to this, and I will have k internal here. Okay? And when I look at such a term, it is k internal divided by epsilon squared. Bakın tahtayı ne kadar güzel kullanıyorum. Biraz daha olsa duvara yazacağım aşağıya. E to the minus j2 theta. Okay? So this is my magnitude at this part. And when epsilon goes to 0, this is going to infinity. Okay? The magnitude goes to infinity. And what about minus 2 theta? Minus 2 theta is going to start from 0, and it's going to end at minus 180 degrees. Because of the minus sign, this is increasing, this is going to decrease. So meaning that I'm going to start at 0 angle, and I'm going to go to minus 180 degrees. Because this is decreasing, I will go in clockwise direction. Okay? So this part of the Nyquist plot is going to be the part from A to B. And the other part is frequency response. And what about this part? It is right at 0. Okay? It is this part. And the other part is just the symmetric component.
How do we know if k internal is negative or not?
So here, when we started with the topic of Bode plots or the relative stability part, we actually talked about the fact that we always assume in this part k internal is always positive. We are also always assuming that there are positive signs here. We are never assuming in a Bode plot. We are never using a 0 or pole in the positive real part. Okay? So in this part of the course, with the Bode plots, when you are given a Bode plot, you can really assume that all of the poles and zeros are in the open left-out plane. Okay, so you can actually assume this. Either on the roots are going to be either on the imaginary axis or in the open left-out plane. You never try to make a Bode plot analysis for a system with poles or zeros in the zeros can be in the right-out plane sometimes, but we never try to do that for systems with right-out plane zeros or poles. Yes.
Does it affect the Nyquist plot?
No, in Nyquist plot we can have both. Okay, so that is the generality of the Nyquist criterion. This is only for the Bode plot parts. We always have positive signs here, and we always have a positive internal gain for the Bode plots. Otherwise, the Bode plot would be meaningless. It wouldn't make much sense to draw Bode plot when there are minus signs here, or when you have negative gains. In that case, phase margins, gain margins, they would lose their meaning, okay, from the Bode plot. But in the Nyquist plot, everything is possible. Okay. So here, what does this mean? This means that we have got the Bode plot. Instead of the Nyquist plot of this thing, we got the Bode plot. And based on this Bode plot, we can actually design our controller. Okay? So the first task is not to extract the transfer function from this, because we can never do it without using a computer. Okay? It is not going to be a very good transfer function when we try to extract it. Instead, we can actually try to read some points from this Bode plot, and actually such a Bode plot can be experimentally obtained. Okay? Extract g of s from the closed loop system, give it some sinusoids to that system, and look at the sinusoids at its output. And look at the phase change and the magnitude change in the input and the output. And you can obtain this Bode plot experimentally actually. You can obtain some points on it, and then you can interpolate to draw such a Bode plot. Okay? And when you obtain such a Bode, why do we do that? Because we don't know the systems that we would like to control. We don't know the transfer function of the system that we would like to control. When we don't know the transfer function, either we have to do something to obtain that transfer function, or we can obtain a Bode plot instead, and we can try to work out our controller design without knowing the transfer function at all. So far in the phase lead and phase lag compensators, we have actually designed our compensators by knowing g of s. G of s was given to us, and that was the analytical design. Okay? So today we are going to be looking at the graphical design, okay, instead. So we only have the Bode plot. Without knowing any transfer function of the system, G of S, we will be able to design our phase lead and phase lag compensators. The first thing that we are going to do is to design a phase lead compensator, and the requirements for that is that we want steady state error smaller than or equal to 1/75, and we want phase margin larger than or equal to 30 degrees. Okay? You know that this is the steady state error requirement of the system, and this is the transient requirement of the system. Phase margin is approximately related to the damping ratio of a closed loop system. And we really do not want a very small phase margin. If it is very small, then that means that the damping ratio of the system is very small, meaning that the oscillations and the overshoot will be really quite bad. So based on these requirements, we are going to now design our phase lead compensator. What is a phase lead compensator? We have the transfer function 1 plus Ts divided by 1 plus alpha Ts, and alpha is between 0 and 1. Okay? So that is our phase lead compensator, and here T is a positive number. When with these parameters, this compensator has the magnitude waveform, which is looking like this. This is 1 over T, and I have 1 over alpha T here. And when I look at its phase is looking like this. It is always positive. It makes a peak somewhere in the middle. And here, this point is my omega m, and here I have my positive phase here, which we are going to use. In the phase lead compensator, we benefit from the phase, and the magnitude is a side effect that we would like to overcome. Okay? When I look at this omega m, it turns out to be the geometric mean of these corner frequencies of numerator and the denominator. So it is 1 over square root alpha t. And when I look at this phi max and alpha relationship, alpha is 1 minus sine phi max divided by 1 plus sine phi max. This alpha is between 0 and 1, and such a number would be always between 0 and 1. And finally, phi max is between 0 and 90 degrees. That is why this sign is always a positive number. And finally, we have this magnitude at the peak phase, which is 20 log 1 over square root alpha. Okay? Now we can actually start designing our phase lead compensator. What does the design mean? Design means I have to know these unknown parameters, unknown parameter k, and unknown parameters alpha and t. Okay, I have to know those. I have to find those to satisfy these error requirements. Okay? The first thing that we do always is to satisfy the steady state error requirement. In order to satisfy the steady state error requirement, I need to adjust k. So here, this steady state error for unit parabola input, or unit acceleration input. So here, if I want the steady state error smaller than or equal to 0.11 over 75, what should be my Ka value? We know that the steady state error for unit parabola input is 1 over Ka. Okay? If I want this number to be 1 over 75, what should be Ka? Ka is going to be 75, okay? And I know that Ka is defined as limit as s goes to 0, s squared, gc of s, and g of s, okay? That is what Ka is. And when you let s go to 0 in this compensator, we see that this becomes 1. Okay? That means that the compensator really does not contribute to anything to the steady state error. Okay? And that actually means that I can only consider this s squared term and g of s term. And now we can actually try to find what k should be in order to be. I have forgotten something here. What is that? I have forgotten k. Obviously, this is open loop transfer function. So I need to put k there. Okay? So I see that in order to set Ka at 75, I need to look at limit s goes to 0, then I have s squared k times g of s. So I need to know something about g of s, and from this body plot I can extract that something. Okay? So now let us try to look at what g of s looks like. I need an approximation for g of s at low frequencies, because here s is going to 0. That means that I need an approximation for g of s at low frequencies. If you look at the slope here, when the frequency increases 10 times, from 210 to the minus 2 to 210 to the minus 1, how much decrease do you observe at low frequencies? 40 dB. So that actually means that this system is a type 2 system. This system is a type 2. So that actually means that I have an s square in its denominator. And I can have some, at high frequencies, I have some poles, T1s, 1 plus T2s, going like this, and I have 1 plus tau 1s, 1 plus tau 2s, etc. I have some zeros. But from this body plot, I will never be able to extract the information for this tau 1, tau 2, T1, T2, etc. I really do not need to either, okay? Because at low frequencies, all of these terms will become 1, okay? At very low frequencies, below all corner frequencies, around here, low frequency region of the body plot, all of these terms will bring 1 to us. Okay, so they are not really important at low frequencies. And here I have k internal. I can have k internal of the system. In my notes, sometimes in my notes earlier, I have used k original here instead of k internal. It's the same thing. Okay. So here at low frequencies, I can really approximate this g of s as k internal divided by s squared here. And when I look at and here, what would the result be if I take the limit of s squared k g of s? What would be this limit with this approximation? Yes, it is going to be k times k internal. So I have k times k internal should be 75 for me to satisfy the steady state error requirement. Okay? So here, one mistake would be to forget this k internal. If you forget this, and if you equate k to be 75, then things are not going to go well after that point. You should never forget this k internal. But here, how can I find that k internal?
Looking at an arbitrary point.
Yes, concentrate on the body plot at low frequencies and try to read the magnitude value. At low frequencies, g of j omega is going to be looking like k internal divided by omega squared. This is the magnitude of g of j omega. And then if I concentrate on some low frequencies here, where the effects of these poles and zeros are not visible, if I can concentrate on this part of the body plot, by reading some values from there, I can extract what k internal is for this system approximately. Okay? So here I generally try to concentrate on one of the intersections here. There is an intersection here with 40 dB line here. What is this frequency?
5 times 10 to the minus
5 times 10 to the minus 2. So if I look at this, k internal times 5 times 10 to the minus 2 squared, it is 25 10 to the minus 4 is equal to what?
100.
It is 40 dB, and 40 dB is 100 in linear scale. That actually means that k internal is 0.25. Okay? And then what I can do is that I can substitute it here, k internal. This is 0.25, meaning that k should be 300. Okay? So that actually gives us the required k value. Okay? K is 300. Okay. And I'm going to need this number in dB scale. Because in the next step of design, I am going to combine K with G of S. Okay? Remember, in our design, we combine K and G of S, and we call it G uncompensated of S. It is K times G of S. Then what I need to do is to obtain the Bode plot of G uncompensated of S. I am already given the Bode plot of G of S, and how should I draw the Bode plot of K times G of S? What is going to happen there compared to Bode plot of G of S? Shift the magnitude by this K value. So for that, I need to look at K in dB scale. Okay? If I take 20 log 300, okay, this is 20 log 3 plus 20 log 100. This is 40, and this is approximately 10. Then this means that I have 50 dB gain with K. Okay. So K is 50 dB. Okay. That actually means that I'm going to shift this magnitude plot by 50 dB up. Okay. And then what about the phase plot? A single gain, a positive single gain, does not have any phase. That means that the phase plot is going to remain the same. Okay. So here I have that plot shifted by 50 dB. Okay. So the difference between the earlier plot and this plot is 50 dB. Now, as one of my design steps, I will try to find the phase margin and the gain crossover frequency of the uncompensated system. So currently, this is K times G of S. This is the uncompensated system. Currently, I haven't added the effect of GC of S to this system. So now what we need to do for designing a phase lead compensator is that we need to find the actual phase margin of the uncompensated system here. For that, I'm going to find the uncompensated gain crossover frequency. This is called omega G, and it is where the gain of the uncompensated system is 1 or 0 dB. Okay? I'm going to look at where this plot crosses 0 dB. Okay? It is here. If I look at this plot, then I'm going to be looking at the intersection with 0 dB. If I concentrate on this plot instead, where should I look at the intersection? Where should I look for the intersection with this plot? Minus 50 dB in that case. It's going to be here again. Okay? So here, the uncompensated system gain crossover frequency is, what is this frequency? Yes? It is 20. So I can actually write, this is 20 radians per second. So now I'm going to look at the phase margin of the uncompensated system. That means that I'm going to go here to the phase curve, and I'm going to read the phase here. Approximately, what is this number? Minus 190 here. How can I obtain phase margin from this? I'm just adding 180 to that. Okay? So what is the phase margin of the uncompensated system? It is minus 10. Phase margin uncompensated is minus 10. Approximately. Okay? So here, as long as you stay in reasonable approximations, you're going to be fine. That number is not minus 190 exactly, but it is close enough for me. Okay? So I have minus 10. So what can you say then about the stability of the closed loop system without this compensator? It is unstable because phase margin is negative. Okay? So phase margin and gain margins should be positive for a stable closed loop system. Okay? So without the compensator, I have an unstable closed loop system. So now I'm going to find here how much phase should I add to the system to get this requirement satisfied. Okay? How much phase should I add to the system to satisfy the phase margin requirement? Remember, we get that number as follows. I have phi max is equal to, I have required phase margin okay, minus uncompensated phase margin. Remember here, when I add this phase to the system, there is also a magnitude added to the system. This magnitude, actually, positive magnitude, shifts this frequency to the right, unfortunately. And that causes a decrease, further decrease in the phase. In order to be able to avoid that phase decrease, I'm adding a 5 degree of error margin here into my calculation. Required phase margin is 30 degrees, minus uncompensated phase margin is minus 10 degrees. And I add here 5 degree of error margin, then this is going to give me the number phi max to be 45 degrees. Okay? And when I use this phi max, alpha is given as 1 minus sine 45 degrees divided by 1 plus sine 45 degrees. Okay? So here, when I calculate that number, you're going to end up with something approximately equal to 1 over 6. I have already found my alpha, okay, which is going to be 1 over 6. And now in the next design step, what I have to do is that I need to choose this frequency, peak frequency position in my frequency axis. I need to place this peak frequency at the new gain crossover frequency of the system. Okay? I need to place the peak frequency there at the new gain crossover frequency of the system. Why do I not add it to? Why do I not choose omega m is equal to 20 radians per second? If I choose omega m is equal to 20 radians per second, then what is going to happen is that the new gain crossover frequency is going to be somewhere here. Okay? Because of this positive phase added at that frequency. Okay? My new gain crossover frequency will no longer be 20 radians per second. Okay? So I need to place this omega m at the new gain crossover frequency. So here, how can I find the new gain crossover frequency? At the new gain crossover frequency, magnitude of G, or G uncompensated, of J omega GC, that is the new gain crossover frequency, times the compensator magnitude. It is G, I have C, J omega GC at the new gain crossover frequency. This magnitude should be equal to 1, or it should be 0 dB. Okay? So here I have the magnitude of this compensator at the peak frequency is 20 log 1 over square root alpha. Okay? So what is this magnitude here at the new gain crossover frequency? I want to make omega GC is equal to omega m. Okay? And at omega m, this magnitude is 1 over square root alpha. Okay? What should be the magnitude of the uncompensated system to satisfy this equation? Square root alpha. Okay? So this actually means that at the new gain crossover frequency, G uncompensated of J omega GC should be square root alpha. Okay? That is 1 over square root, sorry, this is 1 over square root 6. Okay? I have the body plot there. Okay? So I can actually calculate this number in dB scale. If I calculate this number in dB scale, it is going to be minus 10 log 6. And log 6 is, this is log 2 plus log 3. This is approximately 0.5. This is 0.3. So minus 8 dB. Okay? Now I'm looking at where the uncompensated system magnitude is at minus 8 dB. Okay? Where is my new gain crossover frequency? Where is the uncompensated magnitude? Uncompensated system magnitude crosses approximately minus 8 dB. It is somewhere here, right? So this is approximately minus 8 dB. What is this frequency? It's 30 radians per second. So omega GC is equal to 30 radians per second. What I have to do is that I need to equate this number to 1 over square root alpha t. Okay? And that's going to give me what t should be. T is equal to 1 over, I have square root 1 over 6 here, and I have 30 here. This is going to turn out to be approximately 1 over 12. Okay. And then I can try to find the compensator transfer function by substituting this t here and substituting alpha t here, which is going to give you the overall transfer function of the compensator. Any questions here?
Hocam şeye bakacak mıyız peki error margin'in içinde olduğu mu?
In general, you can try to check it, but what is important for me is the main design.
Sanki içinde 5 derecenin içinde değil.
Might be. In that case, what would you do? What would you try to do? Increase this 5 degree error margin. If you increase that, but in that case, what is going to happen is that this alpha is going to get larger as well. Okay, so then you have to check once more if it is in the boundaries or not. So if phase of the system, if this thing is decreasing quite sharply around the gain crossover frequency, then sometimes it's impossible to design phase lead compensator. Okay, so while satisfying the requirements. Any questions? Yes.
Hocam, instead of giving some error margin, can we adjust the gain with in the uncompensated gain phase crossover, not gain crossover, we can adjust with k, gain of the compensator itself, the magnitude.
Yeah, that by adjusting the gain, we are going to do a similar thing. For example, this system. That is the original system. Okay, so this is the original system, and this one is with k. Okay, so then how can you, by increasing the gain, if you decrease the gain here, then the gain is going to be decreased throughout all frequencies. Okay? Then you will lose the steady state error performance in that case. If you decrease the gain to increase the phase margin, then if you decrease the gain, you will lose the steady state error performance. Okay? If you increase the gain further, you would decrease the phase margin of the system. So you cannot do it by pure gain anymore. Okay? That is why we use this compensator to actually boost the phase with the phase waveform here, and while trying to overcome the magnitude increase. Okay? With pure gain, you can no longer do it. If you choose your gain smaller, the phase of the system is going to increase, but steady state error performance, you will decrease this waveform at low frequencies as well with a single gain. Okay? But we can do the same thing with something called phase lag compensator. If I can decrease the gain only somewhere around here, and if I can keep the gain the same at low frequencies, then I can always achieve this. That is called a phase lag compensator. Okay? So remember, in this transfer function, I would still have the same requirements here. But instead of using a phase lead compensator, I can actually try to use a phase lag compensator. And in that case, alpha is going to be strictly larger than 1. In the phase lead compensator, alpha is between 0 and 1. And here in phase lag compensator, I have alpha larger than 1. Okay? So in this case, t is still larger than 0. Okay? Now let us try to look at the phase lag compensator, where we are going to use the gain only to be able to achieve our performance requirements. So when I concentrate on the phase lag compensator, then the magnitude is going to be just the reverse of the earlier case. This is 1 over alpha t, 1 over t now. And when I look at the magnitude, I will get this thing. Okay? Now, as you see, this compensator reduces the gain at high frequencies, but it keeps the gain. When I add it to this system, it is going to reduce the gain at high frequencies, but it's going to keep the gain magnitude the same at low frequencies. So steady state error performance will not change, but I can play with the gain amount here to change the actual phase margin of the system. Okay? So here, what is this magnitude here? Let s go to infinity in this transfer function. What do we get? This is 20 log. Let s go to infinity there. It is going to give you 1 over alpha. Okay? And when you look at the phase, you get the following waveform. Now the phase becomes completely negative, and it's going to be something like this. And you won't need what phi max is here. It's going to be given with a similar formula, but I won't calculate. We really do not need it. So now, in the phase lag compensator, we are using the magnitude to adjust the phase margin of the system. And then the phase becomes a side effect. Why is that? Because this is reducing the phase. It can actually reduce the phase margin of the system. Okay? That is why we're going to try to benefit from the magnitude, and we're going to overcome the phase decrease as a side effect. Okay? So now if you look at the design steps for the phase lag compensator, we have exactly similar steps. We first adjust K to satisfy the steady state error requirement. And we can do the same operations as before, and we can obtain K is equal to 300, which is equal to 50 dB. And then what we can do is that we can shift the magnitude by 50 dB, and we can obtain the uncompensated system magnitude and phase. Okay? So these steps are exactly the same in phase lag compensator design. And now what we can do is to find the new gain crossover frequency of the system directly. How do we do that? We actually do it as follows. So suppose that we can reduce the gain of the system by this amount. Okay? This is the uncompensated gain crossover frequency of the system. If I can reduce this frequency a little bit, I see that the phase of the system increases automatically. If I can reduce the gain crossover frequency, then phase of the system actually increases by itself. Okay? And then I can try to adjust my new gain crossover frequency somewhere here, okay, so that I have the required phase margin here. Okay? How do I find our new gain crossover frequency? So here we want 30-degree phase margin. Where should the uncompensated system? Where should the compensated system magnitude cross at the gain crossover frequency? At which phase should we cross here? Bunu söyleyemeyeceğim. So here I'm trying to adjust the phase margin of the system at 30 degrees. Okay, so that my phase should be minus 180 degrees plus 30 degrees. Okay, so the phase should cross minus 150 degrees at the new gain crossover frequency. Okay, but here, as you might remember, this phase, I'm going to try to place this magnitude and phase somewhere here. Okay, and in such a case, there would be still a negative phase here that might affect the phase of the compensated system just a little bit. That is why here I will choose my new gain crossover frequency such that G uncompensated at the new gain crossover frequency, this argument, is going to be minus 180 degrees plus 30 degree required phase margin. and I will add a 5 degree error margin here. Okay? So now this is going to give me minus 145. Okay? Then I'm going to place my new gain crossover frequency where to the frequency at which we have the phase of the uncompensated system equal to minus 145. Okay? So here, if I look at this phase, so I see that here, somewhere here is I have minus 150. Okay? So then I have minus 140 something, and here it might be minus 145. Okay? Is there any other place that I can place my my new gain crossover frequency? There is also somewhere here. So I can choose both of them. Okay? It really doesn't matter. You can choose any one of them. But here I will choose the right one. Okay? Because here it's going to require less gain I need to reduce this gain with a smaller amount to achieve this new gain crossover frequency. Okay? I need to use a larger gain to reduce the gain crossover frequency to here. Okay? So instead of this, I will try to choose this. What is this number? What is that frequency? It is 6 radians per second. Okay. Teneffüse bir 10 dakika geç çıkabilir miyiz? Sonra 10 dakika size veririm. Şimdi burada kesersek ondan sonra toparlaması tekrar zor olacak. Okay, I need to make 6 radians per second my new gain crossover frequency. Okay? If I go to 6 radians per second, I will get somewhere here. Okay? The system has some positive magnitude in dB scale here. How can I make this point my new gain crossover frequency? I need to reduce this gain to 0. I need to pull this to 0 by using that compensator. I need to use this negative magnitude here to reduce the gain at that frequency to 0. Okay? Now what is the gain of the system at that frequency? G of, I have uncompensated at J omega GC. Okay? What is the gain there at 6 radians per second? So approximately what is this?
17.
Yes, in my notes I think I take it 16 dB. Okay? The system is going to bring 16 dB. Okay? The compensator is going to bring 1 over alpha. Okay? Compensator is going to bring 1 over alpha magnitude. The system is going to bring something. So I need to write here this. G uncompensated of J omega GC times G compensator J omega GC should be equal to 1. Okay? This is 1 over alpha at the new frequency. Okay? What should be this in terms of alpha? It should be alpha itself. Okay? So here we see that here I have alpha should be G uncompensated of J omega GC. Okay? And I have read what that value is. It is 16 dB. So alpha is going to be 16 dB. How can I calculate the linear scale magnitude here?
10 to the minus 20.
Yes, it is just going. I'm going to divide this by 20, and then I will look at 10 to the 16 divided by 20. Okay, that is what the magnitude in dB scale is, and that is going to give you alpha 6.4 approximately. Okay. And finally, what I'm going to do is that I will try to place this larger corner frequency at least 1 decade below the new gain crossover frequency. I want this phase decrease to happen somewhere here. I really do not that phase decrease somewhere here close to the gain crossover frequency. That is why I need to place this thing at least 1 decade below the new gain crossover frequency. That is why I choose this larger corner frequency, 1/t, at least 10 times below the new gain crossover frequency. Okay? So that actually means that t is going to be 10 divided by omega gc, 6.4, which is going to give me approximately 1.7. Okay? So then this actually completes the design, and I can substitute these numbers to where they belong in my compensator transfer function, and then I can put this system into my loop, and then I can try to look at the step responses.
Hocam,
Yes.
sizin alfa 6.4.
Efendim?
Ise 10 over.
Yes, this is wrong. This is 6 radians per second. Okay, thanks. So suppose that I use the phase lead compensator and phase lag compensator, okay? And I suppose that I put them into this closed loop system, and suppose that I look at the step responses of these two closed loop systems, okay? When you do that, you're going to get something like this, okay? So the red curve belongs to the lag compensator, and blue curve belongs to the lead compensator. Why are they different? Remember, phase margin is related to the damping ratio of the system, and the damping ratio determines the overshoot. Okay? What can you say about the overshoots of these two systems? They're almost the same. Okay? So the overshoot, because we adjusted the phase margins with the same requirement, the overshoots of these two systems are the same. But one of the systems is much slower. Why is that? So remember that I talked to you about the following. Control systems in general are low-pass systems. Okay? If I look at the closed-loop system frequency response, what we usually see is something like this. Okay? So these control systems are low-pass systems, and closed-loop system is something like G over 1 plus G, and G is the open loop transfer function. Okay? And a cutoff frequency of the closed loop system is usually determined by the gain crossover frequency of the system. Okay? So this is the gain crossover frequency of the open loop that is read from the open loop system. But when you look at the closed loop frequency response, you will get something like this, and the cutoff frequency is going to be approximately the gain crossover frequency of the system that you adjust. In phase lead compensator, so we have something like this. This is the uncompensated system. In phase lead compensator, the new gain crossover frequency was 30 radians per second. Okay? So we increased the gain crossover frequency of the system. So when we actually use a lead compensator, we increase the cutoff frequency of the original system. Okay? The closed loop system becomes a low pass filter with a larger cutoff frequency. Okay? And when we look at the lag compensator, in that case, we decrease the gain crossover frequency of the system. Okay? So a lag compensator would give us a low pass filter with lower cutoff frequency. Okay? So if you have a step input, if you give a step input to a low pass filter, what type of response would you expect? So if you give it to a system like this, it's a low pass filter with a frequency response like this. Suppose that you obtain something like this. Okay? This is my response for the middle low pass filter. If I increase the cutoff, so here we see that this sharp change is filtered this sharp change here in the input is a high frequency component. Okay? If we filter it with a low pass filter, it is smoothed out here. Okay? In the response, you won't see that sharp change, so your response is going to be looking like this. Okay? For the low pass filter with the red frequency response, the response is going to be faster or slower. It is going to pass more high frequencies. Okay? This sharp change is going to be less smoothed in the red low pass filter. Okay? So the red response would be looking like this. And if you look at the green response, it's going to be even slower. Okay? It's going to be looking like this. Okay? So in some way, a lag compensator, because it makes the cutoff frequency of the system smaller, gives us a sluggish, a slower response at the end. That is why we observe this slow convergence here with the lag compensator. With the lead compensator, we get a faster response. So why do we not use lead compensator always then?
Realization in the real physical.
No, it's not related to realization. Both of these lead and lag compensator can be realized by using passive components, resistors, capacitors, inductors. We can make them passive components. So no difference between realizations. There's something more. Yes.
There are some systems which is really hard to solve the stability.
Yes, sometimes if the phase is, for example, decreasing quite sharp, then phase lead compensator might not be possible. Also, if the phase is not passing from the required point, phase lag compensator might be impossible. Okay? But there is also a reason related to the compensators here. Suppose that you have some noise in your system. Okay? So suppose that if you have some noise, which is let us say that it's a white noise which is covering all of the frequency ranges here. In that case, increasing the cutoff frequency of the closed loop system will result in more noise entering into your system. Okay? If I add some noise to both of these systems, the noise response of this blue curve is going to be much worse, because noise is going to be passing from that low pass filter much more than the lag compensator. This is also the reason why PI controller, for example, PI controller is used much more than PD controller in control systems with some noise. In power electronics, for example, if you want to control an electric motor, usually you choose a PI controller over PD controller. Because PD controller, because it has a derivative inside, it amplifies noises. A similar thing happens in phase lead compensator as well. Okay? So you choose lag compensator, which is more like a PI controller in your system, rather than lead compensator if you have more noise in your system. So let us give a break. 53 geçe tekrar başlayabiliriz. 53 geçe. Evet. Şöyle, şimdi ben açı nasıl ölçüyorum? Açı pozitif veya eksen. Negatif.